So this is the first video of a series that I'm doing where I explore number theory, conjectures, theories, patterns, and stuff. So in this video, I wanted to start off easy to explore palindromic primes. So this is an open conjecture, and we want to know whether there are infinitely many palindromic primes or not. So basically, a palindromic number is a number that when you read from the left and from the right, it reads out the same. So we have, if we have like 001, this is palindromic. Because no matter where you start reading, it's gonna be the same number. Okay. Now let's list out some palindromic primes. 2, 3, 5, 7, 11, 101, 131, 151, 1, 2, 2, 3, 3, 3, 2, 2, 1. This is also a palindromic prime. And the biggest one that we have ever found was 10 to the 1888529 minus 10 to the 944,264 minus 1. So these are all examples of palindromic primes. Interesting, right? Well, we actually know that none of the palindromic numbers other than 11 will have even length. By length, I mean the amount of digits. So 101 contains 3 digits, and so it has a length odd. Its length is odd, but for 11, it is 2, which makes it even. And the reason is actually about the divisibility rule. If you know about it, you can already see why, but if not, here's some. Assume a number it has even length. So we can actually, let me give you an example. A, B, B, A. Let's say this is a palindromic prime, right? Now let's say we have A, B, B, A. We can write this as the first digit. No, let's start from the very far left. 10 to the 3 multiplied by A plus 10 to the 2 multiplied by B plus 10 to the 1 multiplied by C plus 10 to the 0 multiplied by A, and I kind of made a mistake here. This is gonna be B. Now we have this, right? This is pretty obvious. These two numbers are equal. When you divide this number by 11, right? This is gonna give you a remainder of A. So we are doing modular arithmetics in here. This is gonna give you a remainder of minus B, because 10B is congruent to minus B mod 11. So if you don't know any modular arithmetics, I encourage you to learn it. It's pretty interesting and we use it a lot. This thing is gonna be B mod 11, and this thing is gonna be mod minus A. Mod 11 is gonna be minus A. And when you add these up, these all are gonna cancel each other, meaning we get 0, which is 11 divides 0, so this number is divisible by 11 for any palindromic number bigger than 11. That's why the palindromic primes are gonna be odd. Now using this, right, we can write a palindromic prime number as this. So let's say P equals to, let me give you an example for clarity. ABA is equals to, so ABA is just an example palindromic prime. We can write this as n equals to 0, m minus 1, 10 to the n, e to the en. So what is m? M is the amount of digits that we have. In this case, it's gonna be 1, 2, 3. So we go from n equals to 0 to 2. We have 10 to the n, which we already wrote it in here. Well, it holds. And en is the series for which we start from the first digit, we go towards the left, and we list out the digits is the elements of our series. So En is equals to A, B, A in this case. And for ABC, En is gonna be equals to CBA. Oops. Yeah. So this holds, we can see. And something pretty interesting, I also want to share this too. Where's my mouse? Up here. So something pretty interesting is that when we write, oops, this, right, when we write this, not m minus 1, this is gonna be, oops, this is gonna be m over 2 floor. So this is the floor function, basically rounds down the number. So 10.05 floor is equal to 10. 10.5, if you take the floor, it's going to be equal to 10. You will just run down, you just remove the decimals. Now, m over 2, we know m is odd, right? Assuming this number is bigger than 11, m is odd. And when you take m over 2 and round down, you are excluding this final digit, right? Because m is equal to 3, divided by 2 to get 1.5, round down to get 1. So we go from n equals to 0 to 1. N equals to 0 is here, n equals to 1 is here. So we just remove the final digit in here. In a case where we had A, B, C, B, A, we would have removed these two digits. So basically, we get the first half of our number, and by using this, we can create the palindromic number by reversing this number. So that's something interesting that I want to share. This is gonna be, for example, PA, and if we reverse BA, we are gonna get AB, and by combining these two, we can say ABA. This is something interesting that I want to share. It probably doesn't reveal much, but it's still interesting. Now, what's more interesting is primality testing. Well, these are the tests for which we try to find whether a number is prime or not. And there's also a test called as Wilson's theorem, which says that if p is prime, then it will satisfy this expression, right? So this, again, we use modular arithmetics. If you don't know any of it, like, again, I encourage you to learn it. Now, using this, if we plug p equals to what we found here, right, you would get n equals 0 and minus 1, 10 to the n, e to the n minus 1. So this is in parentheses. Factorial is congruent negative 1 mod p. Yeah. If we somehow find the series en and n minus 1, then we can for sure check whether this prime or not using this theorem. But what we can do is actually we can define factorial. So there's definitions out, but since we are working on integers, let's keep the definition of factorial simple. X factorial, let's just say for k equals to 0 to x minus 1, let's say x minus k. So this is one of the most basic definitions of factorial that we can make. This is not true for every number. Obviously, x should be in z plus. By using this definition that we just created and doesn't work for every number, it is bad, I know. There are better definitions out there, but for the sake of simplicity, let's go with this. And we can replace the factorial, so we can plug x in here to get, oh, this is gonna be long. Now in this case we say, let's say x is equal to p minus 1, right? Then we would get, oops, k equals to 0 to p minus 2. Remember we said x is equal to p minus 1? Yeah, we say x is equals p minus 2, so we plug um, p variable, we see x in this equation, and on the inside we would get, let's open two parentheses, and equals to 0 to m minus 1. Send to the n e n, well, minus k minus 1 equals to minus 1 mod p. Now we would get this after plugging everything in, right? So we know p is this, right? We found p in here. Using that p definition, we plugged x as p and found this last formula. No, x as p minus 1, sorry. X is equals to p minus 1. Yeah, this should work for finding palindromic prime numbers for some mn, for some en, which en is a series, obviously. But is it efficient? I don't think so. We have factorial. Oh, I forgot. No, yeah. We have factorial, so it's not efficient, obviously. It grows really fast. But I just wanted to share this. I think it's cool to know. And from here, I couldn't advance it further. But yeah, I just wanted to share it. So that's all for this video. Have a great day.